All right, greetings everyone. Welcome to the third part of the video now for section 3.1, finishing up our intro to polynomials. Okay, so let's talk about finding intercepts for polynomials. And before we do that, let's just talk about them in general. And thinking back to stuff we talked about in chapter 2, how do we find each of the following for any function? So vertical intercepts and horizontal intercepts. What does that mean? Well, let's first of all remind ourselves what those are. So if I have a coordinate grid here, and say a function that looks something like this, okay, what are we talking about if we say vertical intercepts? Well, recall those are spots where we intercept the vertical axis. So it'd be this point right here for a vertical intercept. Now recall, or notice, I did not call this a y-intercept, okay? And just to reiterate, as I have in the past, the reason I don't do that is because my output variable is not necessarily y. So if I, for example, had a function like the one we see here where it's j of t, so our output variable is actually j, so that vertical intercept there would actually be a j-intercept because that would be our output variable. Okay, also recall that a vertical intercept always has the form of 0, some number, right? For any point there along the vertical axis, the coordinates are 0, a number. So to find a vertical intercept, because of that, the way we usually do that is we just plug in 0 for an input. Okay, so as an example of that, in our function before, below, j of t, if we want to find the vertical intercept, well, we just plug in 0. So we do j of 0 equals 2 times 0 minus 1 times 0 plus 3 times 0 minus 2, which gives us 2 times negative 1 times 3 times negative 2. If we multiply all that out, that'll be negative 2 times 3 is negative 6 times negative 2 is 12. And if you write our intercepts here as coordinate points, we see that the vertical intercept of this function is at the point 0, 12. Okay. All right, so then what about horizontal intercepts? How are they different? How are they found differently? And so on. Well, as the name implies, horizontal intercepts are places where we intersect the horizontal axis. So, for example, we have this point, and this point here on this function are all examples of horizontal intercepts. And recall that the coordinates of one of these horizontal intercepts is always a number, 0. Okay, and that's true of any point there along the horizontal axis. You always have an input value and the output value will always be 0. So because of that, if we want to find our horizontal intercepts for a function, we can do that by setting the equation equal to 0. Okay, so if we do that in our function down here, j of t, we'll put 0 for the output equals 2 times t minus 1 times t plus 3 times t minus 2. Okay, and so now we're looking for values of t that make this equal to 0. Well, notice that what we have here are 4 things being multiplied, and when we multiply them all together, we get 0. So thinking back to what we talked about in our prereq material, what does that mean? Well, it means one of those things is equal to 0, one of those 4 things, right? Now, 2 can never be equal to 0, so we can actually kind of ignore that. But everything else could, right? We could have t minus 1 be equal to 0, t plus 3 equal to 0, or t minus 2 equal to 0, right? If we solve each of those, and the first one we get t equals 1, second one we get t equals -3, third one we get t equals +2. And those would be part of our horizontal intercepts. But as I highlighted over here, horizontal intercept always has to form a number comma 0. So if we're going to write these out as coordinate points, okay, our horizontal intercepts for this function would be 1, 0, -3, 0, and 2, 0. Okay? All right, so that's finding intercepts. Now, next thing I want us to notice, or look at, is first of all, what is the degree of this function j of t here? What would the degree be? Well, notice we have 3 terms here, t minus 1, t plus 3, t plus minus 2, that all contain a t. And if we multiply that out, I think the highest power we get there is t to the third, or the highest power would be 3. So this would be a degree 3 polynomial. Well, notice for this degree 3 polynomial, how many horizontal intercepts did it have? Looks like it had 3. Coincidence, you think? Definitely not. Okay. So here, this slide summarizes a little bit of what we just saw. So first of all, if we have a polynomial of degree n, so n is just the number for the degree, well, a polynomial like that will have at most n intercepts, horizontal intercepts, or sometimes you see horizontal intercepts referred to as zeros. Notice that it says at most n. So we just had a degree 3, right, which had 3 horizontal intercepts. However, the graphic here says that it could be at most 3. So that tells us that a degree 3 does not always have 3 horizontal intercepts. It could have fewer, right? So we could have a degree 3 polynomial with only 2 horizontal intercepts, or 1, or sometimes, actually degree 3 will always have at least 1. That's what the next thing says. An odd degree polynomial will always have at least 1. Okay? The next thing this tells us is that a polynomial of degree n will have at most n minus 1 turning points. So what does that mean? I'm going to talk about turning points. Well, here I'm going to try to draw a polynomial similar to the one I had on the last. Something like that, right? And turning points are basically locations of local extrema. So meaning local mins and local max. So if you look at this, we see that we have a local extrema there, a local extrema there. So this polynomial here has 2 local extrema. And here we're told that the number of turning points is at most 1 less than the degree. So that's what at most n minus 1 turning point tells us. So because there's 2 turning points here, that tells us the degree of this polynomial has to at least be 3. Now it could be more. It could be 4, could be 5, could be 6, could be 7. Because again, this says that it has at most n minus 1 turning points. Meaning if this was a degree 5 polynomial, right, that would have at most 4 turning points, but it could also only have 3 or 2. It could have fewer. Now, also this polynomial I've drawn here, this red one, actually could not be a degree 4 or a degree 6 polynomial. Why is that? Right, because the tails are going in opposite directions. Okay, so if you notice, if I highlight these, like the tail here, the tail here, they point in opposite directions, so that's like what the odd degree polynomials do. So this one would have to be an odd degree. All right, so let's put this stuff together to guess some degrees of some polynomials. And look at both of these. And in these, we're going to look at both the horizontal intercepts and the turning points. So for the first one there, notice that it has 1, 2, 3 horizontal intercepts and 2 turning points. So what does that tell us about the degree? Well, the degree here could be 3. Let's think about why, right? We see there are 3 horizontal intercepts, and a polynomial always has at most n horizontal intercepts, where n is the degree. So because we're guessing degree 3, it could have 3 horizontal intercepts. There's also 2 turning points, and the number of turning points has to be at least 1 less, or at most 1 less than the degree. Since our degree is 3, we can have 2 turning points. But this one could also be higher, right? This could be a degree 5. Now notice I skipped degree 4 because, again, we see the tails going in opposite directions here. So this has to be an odd degree polynomial. So it could be a degree 5 because there are 3 horizontal intercepts, that's less than the degree. And then there are 2 turning points, which is less than 1 less than the degree. So it could be that, but up here, as you notice, we're looking for the least possible degree. So 3 would be the answer here, since that's the smallest of those 2. All right, let's look at the next one then. So here, I see 1, 2 horizontal intercepts, and then 1, 2, 3 turning points, which then for the degree, well, since there's 2 horizontal intercepts, that means the degree could be 2, but then we have 3 turning points, and that can't be more than the degree. It has to be at least 1 less than the degree. So because we have 3 turning points, that tells us our possible degree here would actually be 4, right? Because that's more than the number of horizontal intercepts and at least 1 more than the number of turning points. We could also say this is degree 6, right? Because again, we see that the tails here are going in the same direction. So this has to be an even degree. And the number of horizontal intercepts is less than 6, and so is the number of turning points. But again, we're looking for least possible degrees, so 6 is out. So our answer here must be 4. So this, the least possible degree of this polynomial here on the right would be 4. Now it could be 6, it could be 8, it could be 10, 12, 22, 46, any of those. But the least degree it would have is 4. All right, that's all for now. Thank you for watching.